last time, let's recall what we were doing. We did linear functions. We did a little bit of vectors. We did dot product, which is the most important concept for us. And then we also discussed angle between vectors, like x dot y is length of x, length of y times cos theta, and then theta is telling you whether two vectors are similar direction or absolutely opposite direction or orthogonal, meaning 90-degree perpendicular kind of thing. So orthogonality for vectors is the dot product is zero. These are mainly what you need to remember. And then we also discussed a little bit of linear functionals. So basically linear function from a vector space to real numbers. And as we discussed that every such function can be written as dot product with some vectors. So f is basically like every such function itself is like a row vector. And then you are multiplying a row vector with a column vector, you are getting the real number. So linear functions themselves are like vectors. We just think of them as row vectors, and the vectors themselves, we think of them as column vectors. That's the difference. Okay.
Yes.
And then there is something called the dual space, which is basically the vector space equal form out of all the linear functions. So that's the dual, and this is like used in the SVM regression and some other regression kind of setup, where you basically think of like you're trying to learn something. You try to learn. So if we assume that the function is linear in some generalized sense, then what all are my possibilities of such functions? And then out of all those possibilities, which one is best fit to the data? So that's the kind of theory we'll come to that later. And then let's move on. So we talked about matrices. So matrices are basically linear functions between one vector space to another vector space. So typically I think of this way. Let's say I have a regression setup. I have some 5 features. So these 5 features are trying to predict some response. Let's say score of a student in an exam or something based on scores in previous exams, score in some high school, some math competition exam, or whatever else you can want. So these 5 features together are trying to explain the response. So then if I create a matrix where each row is basically one student, so each row will have 5 such feature values. And if you have say 1,000 students, then it will be 1,000 rows and 5 columns.
Yes.
So I get a 1,000 cross 5 matrix. So each row, what is basically it is doing is converting the students' performance into some 5 numbers. And these 5 numbers will be used to predict one number. So automatically the linear functional concept comes in. So you are under linear function between these 5 numbers to a single number. So we need a linear functional. And if you do that for all students, we get a linear transformation. So a matrix kind of thing.
Yes.
So, and as we know that each row or each component of the output is like each row is a row vector. So a bunch of row vectors together gives a matrix. So each column, so typically I try to remember this as each column is a feature and each row is a data point or a person or a student.
Is that always done? They don't switch those. They won't put the features on the rows then and then keep the.
Mostly whatever we will cover in this course, no.
Yeah.
This is always, we will keep this way.
Okay.
Sometimes we'll take the transpose of the matrix itself, like you will have X transpose X kind of thing, but the X itself will keep this structure.
Okay.
Okay. So now if the transformation is from a vector space to itself, then you will have as many rows as columns, and that's a square matrix.
But in that example, then that means that you have to have the exact number of students as you have the number of features.
Yes, that's what it means. But remember that matrices are useful in things other than that data kind of. So that is like one way of thinking of matrices.
Okay.
If you recall, we discussed there are 3 ways of thinking of matrices. One is the data thing. The second is just functions, so linear function between vector to vector. And third is a geometric interpretation where a matrix is basically rotating, transforming, scaling, and all those things, reflection, rotation, all those things are matrices.
Right.
Okay, so and we want to connect all these things.
Yes.
Okay, so what I did was I collected some example of matrices which we'll be using. You know probably all this, but let's just go through together. I wrote this before actually, but I don't know before. So easiest is diagonal matrices. So diagonal matrices means basically all the diagonal values are non-zero, or everything off diagonal has to be zero. Like in NumPy, you can just simply write np.dag and then just the diagonal elements 0, 4, 8. So that will give a diagonal matrix where the diagonal elements are 0, 4, 8, everything else is 0.
Yes. Okay.
Make sense?
Got it.
So what the diagonal matrix is basically doing is scaling each of the inputs x, y, and z to some scaling factor. So each of the component gets its own scaling factor, but there is no interaction between them. So
Yeah.
whenever you need something, some setup, let's say you have multi-stage regression, where in a certain stage, you don't want interaction between the features or the intermediate steps. This is relevant for neural network, for example. If you don't want interaction, you have to make the matrix diagonal. So this is a clear way of telling, like, if I have a multi-stage neural network and say from stage 2 to stage 3, I don't want any interactions, then my matrix will be diagonal.
Mm. Okay.
You can reverse the question also. Suppose you are doing the neural network, so you did the training and all that, and you notice that after doing all that, the matrix is very close to diagonal. It's not exactly diagonal, but all the off-diagonal elements are very small. So there are some metrics to measure how close to diagonal a matrix is and all that, but we'll come back. But the idea is that if a matrix is close to diagonal, that means there is very little interaction between the features.
Got it.
Okay. Good. And then we have identity matrix, obviously zero matrix. We have a matrix of ones. This is very useful like sometimes for some regression setup. So I just added it. The other example I really like is the CL matrix, which is 1, 1, 0, 1. What this matrix is doing is basically f of x comma y is the first element will be x plus y, second element will be just y. So it is keeping the y as is, but adding also the y to x.
Mm.
Okay.
Okay.
This is very popular in some biology examples as well. For example, let's say you have some 20 pairs of rabbits, and then each pair of rabbit gives birth to a kid. So
Okay.
you will have 20 adult rabbits and 20 kid rabbits. Next generation, all the kids will become adult, and the adults will give another birth to again pair, and so on. So you have this rabbit population generation kind of stories. You can find some online as well.
Got it.
So they follow this kind of structure. So you try to study this matrix to understand what is the asymptotic growth of those.
These can expand to beyond 2 by 2 though as well, but
Yeah,
like
this can expand to beyond 2 by 2. The 2 by 2 example is like very easy, but
okay.
you can have larger matrices. The idea is that everything below the diagonal is zero,
Okay.
but above there are some non-zero elements which are basically putting weight from one to another.
Got
There
it.
is some interaction, but the interaction is one direction. So A is affecting B. Like the adult can produce kid, but the kid is never going to produce an adult.
Right.
So that kind of stuff. Okay. And then you have reflection. So what this matrix is doing is keeping the x as is, changing the y to minus y.
Mm. Okay.
So basically you're reflecting on the x-axis. So if you have point 3, comma 4, the 3 will remain unchanged because you're reflecting on the x-axis. So but the 4 will become minus 4.
Got it.
Okay. And similarly, you also have matrices for rotation. So if you want to rotate in 2 dimension a matrix by angle theta, it looks like this. Okay. So the diagonal elements are cos theta, the off diagonal elements are sin theta and minus sin theta. And this is a rotation by angle theta.
Oh, got it. Because
These
then
two things are, yeah, sorry.
you could just rotate by 90 and then you'll have a very
Yeah.
extensive.
Yes.
Okay. Got it.
So rotation matrices, this is in 2 dimensions. There are rotation matrices in 3 dimensions and
Okay.
higher dimensions also. We'll study those. So those are called orthogonal matrices, but they don't have nice formula.
Got it. Oh gosh.
Okay. Okay, fine. So,
The
so
point here,
now,
though, being is that
yes,
Sujay, that we can use a matrix in order to manipulate the vector.
yes. We
Yeah.
are using matrix to manipulate vectors, and the manipulation has to be consistent, meaning the linear.
Yes.
So all the manipulation we are doing, a matrix can only do linear transformation. It cannot do something non-linear.
Got it. Okay.
Okay. So that's the restriction, and that creates a lot of stuff. So that restriction is basically the source of all the things that we do.
Got it. Okay.
Let's move on to a couple of other topics. So first we'll do range and kernel and inversion matrix. So these three are very related, so I've just put them together one by one. So let's see what these are. So first is, uh, yeah. So matrix, if you think of as functions, functions have domain and range.
Yes.
Yes. So if I have a matrix, let's say A going from V to W. So if you think of this as a function, so it can take input any vector in V, but the output range may not be all vectors in W. So the range will be a subspace of W.
Subspace of V or subspace of
Subspace of W, because W is in the range side.
right. Okay.
Domain is V.
Domain. Okay. I'm
Make
so
sense?
sorry. No, one sec, Sujay. I'm sorry.
Yeah.
I'm confused on the notation. What does the
Yes.
notation A colon V arrow W? Can you explain that notation again?
Yeah. So this means that A is a matrix that is taking inputs
V.
from the vector space V. V is a vector space, so
Yeah.
collection of vectors. And the output of applying A to any vector V
Is
is in the space W.
got it. Got it. Okay.
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 So that's why you are saying that the V is the domain
Oh,
and
okay.
W is the codomain,
But
and
then it's like
range will be subspace of that.
domain and range mean something a little bit different here than a function domain and range, then I guess.
No, it's absolutely same.
Absolutely. Because I'm understanding like
What do you
domain
think
is
of
where
domain and range in a function? Like, what's your intuition?
domain is where all of the x values exist, and range is where all of the y values exist.
Yeah, exactly. So, except that for a matrix, the x values and y values are both vectors. So, those spaces where they exist has to be vector spaces. So, their
Vector.
name are V and W.
Yes. Okay. Okay.
Okay. So, it's just like the objects itself are big.
Yes. Got
The
it.
objects are not numbers anymore. The objects are vectors.
Vectors. Yes. Makes sense.
And then the matrix, you can think of arrows from the domain space to the
Well,
range
the
space.
objects aren't like, oh yeah, they aren't like point. Wait, but then if it's a line, I'm getting a little, hold on. Let me wrap my mind around it. But if it's like a line, y is equal to x, that's a vector, I guess, too, right? Or a line.
No, we are not thinking of vectors like that. So objects are still points, but the points are in, say, 5-dimensional space. If
Yeah.
V is 5-dimensional, then the
Because
input is a 5-dimensional point, and
yeah,
the output might be a 3-dimensional point. So it's a vector. A is a matrix from R5 to R3,
got it. That makes sense.
and that will be a 3 cross 5 matrix.
Yes. Yes, 3x5 matrix.
Okay. So this is domain and range. Let's take one example where this is interesting. So let's say A is one. One, two, three, four. This is the matrix. Okay.
Okay.
So now let's apply A and then a vector. And this vector, I will take maybe components, maybe X. Maybe X is confusing also E and B. So let's calculate what will be this thing. So you have to multiply this matrix with this vector.
One,
So again, we'll have a vector as output.
1u plus 2v,
Yes.
and then 2u plus 4v.
So I'll just write U plus 2B
Yeah. U plus
and 2 into U plus 2. Makes sense?
times. Yeah. Yes.
Yes. So can I say this is just maybe Z and 2Z, Z and 2Z, where Z is U plus 2V.
Okay.
So you can see like whatever you multiply this vector, this matrix with, you will get output whose y component is double of the x component,
Oh, interesting. Okay.
right? So you cannot create anything other than this type in the range. So range is, so I'll say this is a set of all u z comma v. Make sense?
Oh my gosh.
This kind of vectors.
Hmm. That line doesn't really tell me anything though, right? Doesn't that just say that it's all real numbers?
No, because it's a vector. The range is a like collection of vectors, and those vectors, there is a restriction that the second component, it has to be double the first component.
God. So the range
So another way to write this
the
is I
range
can just
is
write
okay.
1, 2,
Yes. The range is,
some z times 1 and 2.
and then the restriction is z is a real number. Got it.
Yeah,
Yeah. Okay. Okay.
but like you cannot form a vector like say 3 comma 5. You cannot choose u and v such that the output will be 3 comma 5
Yes.
because 5 is not double of 3.
Yes.
Okay.
Got
So
it.
we will say that 3 comma 5 is outside the range.
Oh, now makes sense. Okay, that makes sense.
So whenever you are fitting a linear model, for example, you can only fit to the data which actually lies in the range. You cannot fit to the data which lies outside the range. And because let's say you have 5 features and 1,000 data points, 1,000 students, then your range space is only 5 dimensional, whereas your input space is 1,000 dimensional. So there are very few points very few like actual data possibilities that can actually fit to a linear model. So that's why in a linear model, you never fit exactly to the data. You fit a best fit kind of thing to the data.
I'm
This
con
situation makes sense?
I'm confused on
Just let's,
this makes sense. The range makes sense. I'm
yes,
confused on how this now relates like to our student example. Can you explain that
yes.
part
So
again?
let's think of again. Let's say we have 1,000 students
Okay.
and 5 features.
Okay.
Okay.
Yes.
So this is a 1,000 + 5 matrix we are
Yeah.
multiplying with. And whatever may be the beta coefficients you get multiplied with. So that means we are doing some linear combination of those vectors, but
Okay.
there are only 5 different features.
Yes.
So if you take any kind of combination of those features, there are only 5 different possibilities of vectors, like 5 dimensional space they can create.
Correct.
But the students themselves actual say score in the exam, final exam, that's the response variable. That is 1,000 dimension because every student gets a score. So that's a 1,000 dimensional vector.
Okay.
So out of that having 1,000 dimension vector lives in a 1,000 dimension space
Yeah.
because the set of all possibilities, let's say any student can get any marks,
Yes.
then those thousands are all independent. So there is a 1,000 dimension, like your degree of freedom is 1,000.
Yes, I agree.
So there is 1,000 dimensions, 1,000 degrees of freedom in the possible scores that student can actually get. But because my feature is only 5, the range space is 5 dimensional.
Range.
Because there are only 5 linear combinations I can. There is only 5 degrees of freedom.
That last part's not making sense, Sujay. Like why is that like how would you then restrict that 1,000 dimension space then?
The way I'm restricting is, let's think of this way. So suppose the X matrix is um, X1 up to X5, right? This is
Okay.
my X matrix.
Yes.
And my beta matrix, sorry, beta vector.
Beta is 5.
Beta is a vector. So this is typically a column vector kind of thing.
Right.
So let's say the first is B1. And then like B1, B2, B3 up to let's just write the last one, B5.
Yes.
Now, when you multiply, uh, you
Wait, but
get x beta, right?
your x should go up to 1,000, right?
Yeah, each x is a column vector. So each x is a feature, which is 1,000 length.
Oh, okay.
I've just
Okay.
written x1, x2, x5 as 5 columns of the
Okay.
x matrix.
Okay.
So each of them is 5. Now,
Okay.
when you multiply, you basically multiply the first row with b1, b2, b5, second row with b1, b2, b5, and so on, right?
Yes. Yes.
Which is same as doing b1 times x1 up to b5, x5.
Agree.
This makes sense? Now, the x vectors, you cannot change. You can only play with the b's because those are the coefficients you are like allowed to fit. The
Yeah.
x is already given. So
Yes.
that means you have only 5 free variables in this equation, b1, b2, b5. These are the only ones you can play with.
Yes.
So that means you have 5 degrees of freedom.
That means you have 5 degrees of freedom now. But what you did to do this, though, is you simplified a column vector into a one-dimensional space, right? Like you
No, I
just,
didn't. It's just notation. X is still a vector, but you're not allowed to make any choices inside X.
yes. So you only have 5 degrees of freedom then, because you're only allowed to
Yes.
change the betas.
Yes. Okay.
Yes.
So my point is because you're not allowing to choose the X, you don't get any freedom there. So then your range space is actually 5 dimensional, whereas your
Because
actual
of the
response is 1,000 dimensional.
makes
So this 5 dimension, it's not like it's a length vector. It's a 1,000 length vector, but it lives inside some 5 dimensional space, which is like all the vectors you can create.
Okay, I get this. This
Okay.
makes sense. This makes sense.
Yeah, and this is basically the crux of learning that we do all the time. The
Oh,
learning is that we don't have a lot of freedom in terms of our features and all,
because they're set.
and
Yeah, we
the
can't
actual
change
response
the
can be high. So if you can learn with a small number of features, that means with a restrict constrained scenario, but your response is actually very high dimension, like you fit 2,000 data points, that means your learning is good.
That makes
If you
sense.
use 1,000 features to learn 1,000 data points of 1,000 students, that's basically like you can always get some B's, which is linear combination, and like unless there is some problem in the data, you can always do that. So there is not much learning happening there.
That where that's called fitting, I think, right? Underfitting or
Yeah, that's the fitting part. So if the lesser number of regressors you can fit the data with, that's the better.
which one is overfitting, just so that I know?
Overfitting is when you use too many features.
Too many features is called. Oh, duh. Yeah, that makes sense. Yeah.
Yes.
Okay, wow. Okay, this is
Okay. So
so
this is like the crux of how learning works. The less number of features you use, the better.
this is the crux of machine learning then?
This is the crux of like how good your learning is. Basically.
Learn, what does learning mean? Sorry.
So learning means, say we have a vector y or whatever data we are trying to understand. Learning means
The beta.
in terms of some other variables, we have a way of interpreting we have a way of predicting or
Predicting.
understanding the value of y in terms of x.
That's what I'm understanding too. And then
Okay.
that would be just identifying your betas then at that point, right?
Yes.
Yeah.
Yes.
Okay.
Once you have fixed your model, it's just identifying betas, but you can choose different values of x, different choices of x. Like you may have, like say, 20 regressors. You might say, okay, I want to use only these 5. That is giving me a good enough regression fit. Say, suppose those 5 is giving you a good enough R square, and then another 15, even if you add them, they don't increase your R square much.
Right. Right. Yes.
So that's basically what I'm saying, that then we should not be adding those. They're not adding any value.
Yeah, they're not adding any value. Okay.
And then it's all a game of like what is the row space of the matrix, and whether that row space, your target response is very close to the row space, and how much is the distance.
Okay. Got it.
Okay. So regression is basically trying to find the element in the range which is closest to the response.
Got it. Okay.
So range is what is allowed by the model, and we try to find the point within the range that is closest to the data point, the real data. And that is the fitting part. We choose the B's so that it's closest to what the Y's are saying.
Yes.
Okay, and that's why range is important. And if you can think of the other direction. So suppose I choose from 5 regressors which are very similar to each other.
Okay.
So then their combined range won't be very different from the individual ranges. So
Right.
like combined, they don't cover a lot of stuff.
Yes.
So it's like choosing a team where everyone has same skill. They're all good at only one thing.
Right.
Their combined range is very limited. They can only do one thing. So like whatever the situation may be, there is only one thing they can do. They cannot like cover a lot of situations. So you will probably win some matches, but only some very specific matches you can win.
That makes sense. It'll be good at predicting certain, but then it's not general
Yes,
for, okay.
it's not generalizable.
Okay.
So that's why you don't want to choose a lot of features which are very similar to each other. And that's where the angle between features and all those stuff.
Okay. Got it.
Okay.
Is
And
there a
that's
minimum number of features needed? Like, do you have to have more than 2 features, or can you fit something with 1 feature even?
if one of the features is very close to the response, you can fit with just that.
Yeah, if you
There's no
can.
restriction like that.
Yeah.
Whatever works best. And later on, we'll derive some criteria on how to choose, like whether adding a new feature is good enough. So there is something called information, whether that is adding extra enough, like justifying enough information addition to like add it. So basically, you want to penalize for adding features, but
Right.
you want to give some score that it is predicting R square better or some similar measure to R square better. So you want to give some higher score for that, but you also want to penalize for adding extra feature, and you create some scores out of that. So there is something called AIC and BIC, which are the industry standard for this
I guess
information
that's where the
criteria.
engineering part comes into play.
Yeah, that's where the engineering part comes in, and you try to choose some
Optimizing
combination
the
of features
optimal.
which
Yeah.
is making this best.
There's an art to it then at that point. It's not direct. Yeah. You can choose
Yes,
and stuff. Okay.
yes, exactly. That's what. Okay. So that's the part. The second concept I want to discuss is kernel. So kernel is basically, so you have a matrix A, and suppose you have a vector V, then AV equals 0. Now remember that this 0 is not a vector 0. This is not a number 0. This is a vector 0. Just make it go.
The scalar
Yeah, this is not a scalar.
is not a scalar. Okay.
Yes, this is a vector 0. Uh, so we say that V is in kernel of it.
V.
So if you multiply with a vector and you get 0 vector, then we say that this V is in the kernel or null space of it.
What?
So basically, null space is collection of all such vectors.
Wait, doesn't this have to do with the eigenvectors then?
Yes, exactly. This is like relevant for eigenvector study. But this is not exactly the eigenvector. We haven't reached there yet, but this is related stuff.
One thing, Sujay, just maybe
Yes,
abstracted away. I was looking at like image recognition, and they use the word
yes.
kernel as well there, where it's like the square. Is that related to this? Like the
Can you give me a
kernel
little
is
bit more
like
context?
you can choose a kernel, it said. So you like choose a square, like a small pixel area, and then
Yes.
depending on your pixel area, that's your kernel size or something like that. Maybe not
No,
the
that is a different kernel.
kernel. Okay, okay, got
That's like Gaussian kernel and those stuff, I think.
it. Okay, got it.
So the support vector machines and all those have their concept of kernel,
There's another
but that is a
kernel that
different.
I saw. It was
Yeah,
like,
there is a separate kernel. In the same course, there you have multiple uses of the same word,
yeah, like in
and it will get
Jupyter, you can
confusing.
select your kernel and all that. So, okay.
Yes, yes.
Why is this
Okay.
important then, though? Is it
This is important because, so suppose V is such a vector, okay? Now you are choosing your beta such that, so let's again go to back to the student example. So suppose there is a vector v such that then I can write this. So x beta plus v is x beta plus xv. You agree to this?
Yes.
Now suppose xv is 0 because v is in the kernel. Then this is same as x beta.
Oh, okay.
Okay. So that means uh, whatever beta is predicting, beta plus v will also predict the same.
Sorry, so can you say that again?
Whatever you get, like whatever goodness of prediction you get by beta, you get
Yeah.
the exact same output with beta plus v also.
Yes. I would thought you were going to say the opposite. Whatever you get with beta plus V, you can just do with beta. Why would you want the
Yes.
combination of beta plus?
Yeah, the question is you can also do beta plus 2v, 3v, 4v, and so on. You can do any multiplier. So you get a lot of choices, right?
Yes, but why do we want that V? What is the V?
We don't want that. That's a problem for us. Because if
Oh,
that is happening, if for different beta you get different prediction, then
okay.
you can choose among those whichever is giving me the closest to it, right? That's
So
the
I think
criteria
maybe
we have decided.
the way it should be said then is so beta is equally as good as a predictor as beta plus V then, right?
Yeah,
Because
I just written in the opposite order. I mean,
we
the
want
role
to
of
use
beta and beta plus V. I mean,
yeah.
you can do beta minus V also.
Right,
It's the
right.
same thing.
Okay. Okay.
So the problem is, uh, so beta plus any CV, where C is a constant, are all equally good predictors, right?
Yes. Any
So
constant.
basically, I have given you an infinite collection of predictors, which are all equally good. The question is, how do you choose among them? So we do face a lot of problems like this in our practical linear regression kind of thing, where you get a lot of betas which are equally good. So you have to have a separate way of choosing between them. So we introduce some penalization concept there.
Ah, okay. This is where the penalization comes. Okay.
So